This video explores the link between the signals in biological samples and the digital data from microscope cameras. Understanding this relationship can help you set the ideal image acquisition conditions to achieve the highest quality images and data. First, excited fluorophore or fluorescent protein labels on the target emit fluorescence light. The light intensity increases when more targets are in the sample or when we apply stronger excitation light. Then the fluorescence light enters the camera sensor through the microscope optics and stimulates the photoelectrons in the sensor. Stronger light stimulates more photoelectrons. The photoelectrons convert into a digital signal, which is proportional to the incident light intensity. The detected signal contains actual signal and background signal. The background signal, also known as background noise, can bury your actual signal. If there is no background signal, you can identify any weak signals. To detect your target, you need a high enough ratio of actual signal intensity versus background signal. This is called the signal-to-noise ratio, or SNR. You can achieve a stronger signal in a few ways. Although applying a longer exposure time or stronger excitation light can provide a stronger signal, these changes can worsen phototoxicity if not done carefully. As a result, a common strategy to improve SNR without any trade-off is to use a higher NA objective and a camera with a higher quantum efficiency. To understand quantum efficiency, consider this example. The light intensities are the same for two different wavelengths. But if a camera has a quantum efficiency like this, then the detected signals will differ. Always check that your camera has enough quantum efficiency at the wavelength you need to observe. Now, let's review background signal and its common causes. This is an example of signal from a targeted sample. However, non-specific labels, autofluorescence, or light from the environment can cause background light. Another background signal is the statistical fluctuation of the detected number of photoelectrons. The signal can also be impacted by noises in a camera that contain thermal electrons generated in a sensor. Thermal electrons are stimulated by thermal energy, not by the incident light. The electrical circuit in the camera also causes a noise during the conversion to digital signal. This is called readout noise. Always minimize these background signals so they don't bury your signal. Let's review how to minimize the background signals. First, noise from non-specific labels and autofluorescence can be minimized in the sample preparation and staining process. To reduce background light from the environment, use a darkroom. Statistical error cannot be minimized, but SNR can be improved with a larger number of photoelectrons. To reduce thermal electrons, use a camera with a cooled sensor. Readout noise also depends on the camera, so keep this factor in mind when you choose a camera. Knowing these digital imaging basics can help you improve image and data quality. Maximizing the signal, minimizing the background, and optimizing the sample condition are essential elements to improve data quality for any application or experiment. To learn more, visit www.olympus-lifescience.com.